Hello everyone. Have you ever wondered how powerful mathematics predict future value? For our research assignment, we have chosen to analyze the population dynamics of Costa Rica. Costa Rica provides a fascinating case study for mathematical modeling due to its steady development and unique demographic shifts over the last few decades. The purpose of this task is to determine if a first-order linear differential equation could accurately predict the country's growth. By solving this model, we can estimate future population, determine past values, and compare our prediction with actual data to evaluate the accuracy of the model. So the key question guiding this presentation is, how accurately can mathematics predict the population growth of Costa Rica?
Next, I will talk about the data table. This table shows the population from the year 2006 to 2024. From the data, we can clearly see that the population is increasing every year. However, the increase is not constant. For example, in earlier years, such as from 2006 to 2024 and 2008, the increase is around 60,000, while in later years, like 2021 and 2022 and 2023, the increase becomes slightly smaller. Based on the pattern, the population keeps increasing at a rate that depends on its current value. We can model the situation using an exponential growth equation.
Next, I will be explaining Step 2 and Step 3 and Step 4 of this task, which involves modeling population growth using a differential equation. First, for Step 2, we will let P of t represent the population of Costa Rica after t years. Since this is a growth differential equation, we assume that the rate of change of the population is proportional to the population itself, which gives the equation of dp over dt equals to kp, where k is the growth constant. We solve this differential equation by separating the variables, integrating and exponentiating both sides. We obtain a general solution which is p equals to a times e to the power of kt. Next, we use the given data to find the constant in the solution. From the table, when t equals to 0, the population is 4,818,038. Substituting this value into the model allows us to determine the constant a. So now we have obtained the general solution equation. Then we use the second data point where t equals to 1 and the population is 4,866,998 to calculate the growth constant k. After substituting and solving, we find that k is approximately 0.0101. So the particular solution is now fully determined and we have complete equation that models the population growth. Moving on to Step 3, we use this equation to predict a future value. In this case, we substitute p equals to 9 into the equation. After calculating, we find that the predicted population is approximately 5,276,520. This means that after 9 years, the population is expected to grow about 5.28 million. Finally, for Step 4, we calculate a value from the past. To do this, we choose a negative value of time, such as t equals to -9, and substitute it into the same equation. After calculating, we find that the predicted population is approximately 4,339,394. This gives a population value that is slightly smaller than the initial value, which represents the population before the recorded data. This shows how the exponential function can be used to model real-life population growth.
Next, I will talk about the graph. This graph represents the exponential equation y equal to 481,038 e power of 0.0101t, where t is the number of years after 2015. The curve shows a gradual increase over time, which matches the trend observed in the data table. When we compare the plotted data points with the curve, we can see that the curve appears to follow the general trend of the data points. Since the value of k is positive, it indicates that the population is increasing over time. Therefore, this model can be used to represent the population growth.
Alright, so moving on to the analysis and discussion. So, for the first question, are the values calculated from the particular solution consistent with the actual values? So, to answer this first question, no, they are not entirely consistent. While the model follows the general upward trend, it fails to match the actual data points perfectly, because this particular solution is a smooth exponential curve. It cannot account for real-world fluctuations like migration or policy changes. The visible gaps between our predictions and the actual records show that the model is an approximation rather than a perfect mirror of reality. Alright, so moving on to the second question. How do we calculate the percentage error? To find the accuracy of each prediction, we use the standard percentage error formula, where the absolute difference between actual and predicted values will be divided by the actual population and times by 100%. Now, let's compare the model's performance for the past versus the future. So, for the past, at t equal to -9 in year 2006, our error is 1.806%, showing a slight overestimation, and for the future, at t equal to 9 in year 2024, the error drops significantly to just 0.568%. This proves that while the overall error margin are small, our model is currently more accurate at predicting future trends than reflecting the past. It highlights how the model's reliability shifts as we move further from our 2050 year starting point.
So, based on the calculation, we noticed that there are differences between actual and calculated values. This happened due to several factors. First reason is data collection limitations. Populations data usually based on estimates or surveys, which may not always be 100% accurate. Some people may not be recorded or data may be updated later, causing differences. Second, another factor is assumption used in mathematical model. When calculating population, we usually assume a constant growth rate. However, in reality, population growth is not always constant and can change over time. And finally, external influences such as global trends can affect population. For example, global economic changes or international movement of people can influence population size in ways that are difficult to predict. Next one, what factors influence population growth in the past? There are several key factors. First one, of the main factor is high birth rates. In early decades, especially before the 1970s, families in Costa Rica tended to have more children. As a result, the population increased rapidly during the period. Second one, improvements in healthcare played a major role. Costa Rica developed a strong healthcare system which helped reduce death rates, especially infant mortality. At the same time, people began to live longer due to better medical services. These increases in life expectancy contributed to significantly the population growth. For example, people in Costa Rica now live over 80 years on average. Third, immigration has contributed a lot, especially from Nicaragua. Many people moved into Costa Rica over time and increased the population. And finally, better living conditions such as improved sanitation, nutrition, healthcare, hospitality, and also help the population to grow rapidly. Next, what factors may affect population growth or decay in the future? In the future, population changes in Costa Rica can be divided into two parts, which is growth or decay. First factor is government policies. If the government introduces policies that encourage migration or support families, such as child benefits or better job opportunities, this can increase the population. Another factor is international attractiveness. Costa Rica is known for its political stability, ecotourism, and peaceful environment. This may attract more foreigners to live, work, or retire there in the future. Now, factors that may decrease the population. First, high cost of living. If living expenses increase, people may choose to have fewer children or even move to other countries. Second, environmental challenges. Issues such as climate change, natural disaster, or limited resources may affect living conditions and reduce population growth. In conclusion, this assignment has demonstrated how a first-order differential equation can be effectively used to model population growth. By using real population data collected over a period of time, we constructed a mathematical model and obtained a particular solution that describes how the population changes. While the model provides a reasonable approximation of population trends, some differences between the calculated and actual values were observed. These differences can be attributed to various real-world factors such as migration, government policies, economic conditions, and unexpected events which are not fully accounted for in a simple mathematical model. In summary, mathematics allows us not only to study population growth, but also to better understand the factors shaping our world.